Cash application is widely treated as a straightforward bookkeeping task. In reality, it's a high-dimensional engineering science focused on resolving uncertainty under strict mathematical constraints. The legacy approach relies on a one-to-one deterministic model, assuming every inbound payment will perfectly match a specific open invoice. In a modern enterprise environment processing millions of transactions, that model breaks down entirely. The process is actually a problem of applied statistics. The goal is to find the highest probability match between what a customer owes and what they actually paid. To understand why this is so difficult, look at the left side of this equation, the invoice set. Open receivables are never static. Invoices are issued, disputed, adjusted with credit memos, and subjected to trade deductions, creating a rapidly updating, chaotic list of values in your subledger. On the right side, the inbound payment information is equally unstable. Customers send partial payments, lump sums covering multiple accounts, or omit their remittance text entirely, leaving you with a fragmented, misaligned stream of incoming data. The core engineering objective is to continuously maximize the probability of a correct reconciliation between these two chaotic datasets. Treating this probabilistic puzzle as simple arithmetic is exactly why finance teams end up buried in exception queues. The manual effort required to investigate every mismatch creates bottlenecks that trap millions of dollars in working capital. This uncertainty is driven by specific variables that actively degrade payment confidence. First is information completeness, whether all required data is even present. Second is information accuracy, whether the data provided actually maps to reality. The third, highly volatile variable is time. An early payment, a late payment, or a payment spanning multiple billing cycles changes the accounting reality. Perfect data arriving at the wrong time instantly becomes imperfect data. Because of these variables, every transaction exists on a confidence spectrum. On the far left, you have 0% certainty, requiring full human investigation. On the far right, you have 100% deterministic accuracy. The ultimate target at this end is straight-through processing, or STP, where the system matches and clears the cache with zero human intervention. But here is the mathematical reality. Because the state of receivables and external variables are entirely dynamic, achieving 100% STP is an asymptote. You can get infinitely close, but the changing nature of the data makes absolute perfection impossible. An effective AI engine doesn't eliminate human intervention, requires a structural shift. Enterprises must abandon rigid legacy ERP systems and adopt an architecture built specifically to manage probability. The solution to managing this probabilistic chaos is a fully decoupled architecture. We call this a BAI independent framework. That means it operates independently of any specific business, ERP, industry, or country. By severing the matching logic from the rigid constraints of a legacy ledger, the system gains the flexibility to evaluate data on its own terms. The core philosophy here is radical abstraction. Every single component of the enterprise process is normalized into relational tables. We start with MD Cash App, the master data table, defining universal entities like customer IDs and global tolerances. Above that sits AD Cash App, the activity data table, mapping actual transactional reality, inbound cash and open liabilities, directly to the master entities. Supporting this is the TD Cash App, or technical data layer.
This provides the digital infrastructure, managing the system-agnostic APIs, file ingestions, and the asynchronous event streams that route payloads between upstream banks and downstream systems. To protect the financial ecosystem, the SP Cash App security layer tokenizes all sensitive data the millisecond it is ingested, ensuring the core engine evaluates secure, anonymized payloads. Abstracting rigid ERP structures into these universal tables creates the data environment required to run advanced high-velocity probabilistic mathematics. With the data normalized, we introduce the intelligence layer, LD Cash App, or logics data. This is where the actual matching occurs. The engine leverages Python and Pandas to orchestrate and normalize the raw inbound banking data, transforming messy lockbox files and remittance texts into clean, queryable activity records. NumPy assigns mathematical confidence scores to thousands of invoice-to-payment combinations. Take foreign exchange variance, a €10,000 invoice versus an $11,800 payment. The logic layer instantly cross-references rates, identifies the variance, and applies tolerances. To increase match confidence over time, The logic engine continuously vectorizes historical customer behavior. It remembers that a specific client always pays 3 days late and consistently shorts freight charges, factoring that pattern into the probability score. Transactions that surpass the high confidence threshold are automatically cleared and posted back to the ledger. Everything else is safely parked. The logic layer converts missing, noisy payment information into an automated, mathematically sound financial decision without any human intervention. But we still have to address the transactions that fail the confidence threshold, the inevitable gap to the STP asymptote. This requires the DCID Cash App, the Context Intelligence Engine, which sits directly on top of the data and logic layers. The presentation layer uses progressive disclosure. Rather than overwhelming a user with 50 fields per invoice, the interface shows the unapplied receipt next to the AI's top predicted matches, displaying the exact confidence scores driving the recommendation. An accounts receivable specialist reviews the contextual recommendations, makes a judgment call, and executes a manual override to match the payment. This action triggers the most critical mechanism in the entire architecture, the machine learning feedback loop. Every human override flows backward through the architecture to update the algorithmic weights in the logic layer. Humans are no longer just resolving exceptions. Their targeted interventions continuously train the vectorized memory, teaching the system how to handle that specific anomaly autonomously next time, steadily shrinking the exception queue. When you pull back and look at the fully stacked architecture, from the infrastructure data through the logic engines, all the way up to the user interface, every piece of business, technology, and functional logic is defined in a table. This structural discipline treats the architecture as the operating system for the application. In software engineering, a C compiler reads structural code and turns it into an executable program. TableOS treats these relational data tables exactly the same way, as source code. It compiles the architecture. The system translates the abstract data tables directly into functional application interfaces and processing workflows in real time. This compilation eliminates the translation loss that traditionally occurs when handing abstract business requirements over to a technical engineering team for manual coding. This compiling capability is the foundational engine powering Biflex.com. Biflex.com compiles a continuously learning, applied statistics engine directly from these architectural blueprints, systematically driving the working capital cycle toward total automation.